Everyone is a mechanical expert, or think they are, but electrical scares most people away. This means you likely can do whatever you want in electrical without interference. Electrical is not magic, and once you understand the terminology of components and the intention of design, it becomes much simpler and more understandable. And once you understand both mechanical and electrical power and control, you can begin to take a holistic approach to station design. Appreciate that if there is a significant design mistake, the electrical contractor would be the first to feel the heat of authority. So he has good reason to let you know if you do slip up. Listen to what he has to say. Of course, learning, experience, and baby steps are necessary before you should ever consider sealing a substantial design. If you aren't confident, don't do it. Now, at one time, it was quite common to compare electrical and water systems. In a water system, you've got flow rate, gallons per minute, whatever. You've got pressure, PSI, and you've got resistance. With electrical systems, electrical flow is measured in amperage. Um, the pressure volt is measured in volts, and you have resistance measured in ohms. And the big difference between electrical and water systems in that regard is that in electrical system, the resistance varies directly with the current flow. In a water system, resistance varies as the square of water flow. So in electrical, if you double the amperage, the resistance will double. If in a water system, if you double the current or the flow rate, the resistance will go up by 4 times. Okay, Ohm's law is quite common and ties together uh, voltage as current times resistance. And of course, you can play with that equation to solve any one of them if you know the other two. Now, voltage, which is pressure, voltage, of course, is analogous to pressure, and it's relative. Like with pressure, if you say a pipeline is at 100 psi, that's 100 psi compared to atmosphere. And similarly with voltage, you have to compare between 2 points. If you've got a bird on a wire and it's a high voltage line, then if both feet are touching the same line, the difference between them is nothing and the bird is safe as can be. It's only when he pecks at, say, a grounded transformer that we no longer have a bird to worry about. There's several different voltages, quite a few actually worldwide, such as 380/220 or 220/127 in Europe, but following are the most common voltages in North America, with 120/240 single-phase AC being used in so many houses. Classically, the contractor will bring in 3 wires, a black, a red, a white, and a green. Now, the green is simply a safety for ground. But the black and the red, line 1 and line 2, if you measure between them, you have 240-volt single phase, which means that's used for powering stoves, air conditioners, dryers. If you're between any one of those, either of those lines and the neutral, you get 120-volt, which of course is receptacles throughout the house. And generally they do try to balance so that roughly half the house is using receptacles that go between line 1 and neutral, and the other half is using between line 2 and neutral. Next up is a little sweetheart, 122/8-volt AC 3-phase. Why? Why not? If you take the little symbol and flip it upside down, you can see why it's called a Y. Now there you have 3 wires, 3 hot wires, and a neutral. If you measure between any of 2 of the hot wires, line 3, line 1, line 1 to 2, or 2 to 3, you have 208-volt single phase. Kind of interesting. When these are this distribution, if you have it into your house, what normally would run at 240-volt now has only 208. So the ratings are slightly less. Lower current flow, higher, lower voltage means lower current flow with the resistance, which means you don't get quite as much heat. So this is why you sometimes see dual ratings on a lot of 240, 208 appliances. Now, if you've got in a situation where you're in an industrial area, say a service station that wants 3-phase, you've got 3-phase with this. Line 1, 2, 3. Those 3 wires give you 3-phase. Now, between any one of those hots and neutral, you've got 120. So you can use the system into a residential area and giving them, instead of 240 AC, 208, but still 120 because any line to neutral. Or if you need to run a three-phase motor, you got three-phase 208 volt AC. Now, something that's very not seen much in the US, but quite common in Canada, particularly in British Columbia, is 347-600, which again is a three-phase Y connection. And again, three hots and a neutral, except between the hots is 600 volt. And if you connect with three of them, you have 600 volt three phase. Any one of those hots to neutral is 347 volt. Now, 600 volt AC is really nice for powering pumps and whatever of any size. The 347, you say, what use is that? Well, believe it or not, some stadiums, a lot of stadiums actually use that for lighting and whatever. You can get 347 lighting systems. Okay? And last but not least, 240 and 480 volt three-phase delta systems, where you basically have three wires only, no neutral, and between any of them is 240 volt, and put together you of course have 240 volt AC. Same thing in 480 volt. There are reasons, pluses and minuses, mostly minuses, for going with those systems. Now, frequency and phase. Virtually all industrial electrical systems are based on alternating current, AC, meaning that positive and negative polarity flip back and forth at a tightly set frequency. So does the direction of power flow, of course. Current goes one direction, then the other. The one-time clocks, electric clocks, used that frequency. So that frequency is very tightly controlled by the utility. In North America, the common frequency is 60 hertz. In other words, it flips 60 times a second back and forth between one and the other. While in other countries, Europe, 50 hertz. Believe it or not, at one time, 25 hertz was around. And with 25 hertz, you could actually sit there and see the lights flicker a little bit. Now, because generators are rotating equipment, this alternation is seen as a sine wave, not an instant change back and forth. Okay, it's a sine wave. Why alternating current? Interesting, the current wars between DC and AC, which I won't get into in a moment, but basically AC. Now, AC is actually a result of something I'm going to get into right now, which is very important. Faraday's law, that a voltage is induced in a circuit whenever relative motion exists between a conductor, like a copper wire, and a magnetic field, and the magnitude of this voltage is proportional to the rate of change of the flux. In other words, how fast the two of them are moving. You get that? You move a wire through a magnetic field or move a magnetic field over a wire, you will generate voltage in the wire. This concept of law of induction, of moving a magnetic field, as I say, through a conductor or conductor over a magnetic field and introducing voltage in the conductor, is the basis of a number of electrical devices, including the transformer. Appreciate alternating current applied to a coil will create a constantly changing magnetic field, back and forth, back and forth, back and forth. And that changing magnetic field over a conductor will create an AC voltage. And conversely, that AC voltage on a conductor will create a magnetic field. Okay? As a result of that, you end up being able to make a transformer. Direct current is not changing, so it has no effect. When you first energize it, yes, there's a brief spurt of electricity on the conductor, but that's the end of it. And when it's de-energized, the field, that collapses. But you can see here's how a transformer works. If you look on the left, you've got a number of windings, okay? That creates, that current back and forth on that creates a magnetic field, and that magnetic field carries over to, you see on this transformer, that transformer coil carries that magnetic field over, and when it goes through a bunch of conductors, then it creates a voltage on those secondary conductors. Okay, so in this, there's the basic construction of a transformer. Here's the symbol for it. On the left side, primary. On the right side, secondary voltage. And of course, the transformers we all used to love. Taking that a step further, you have the formula that basically the number of turns, primary and secondary, N1 and N2, will give you the voltages, 1 and 2, and the reverse, because of Faraday's law, current flow varies reverse. For example, let's pretend we're going from, pick a number, let's say 25,000 volt, and we want to bring it down to 600 volt. So you'd have appropriate number of turns on the primary side and a smaller number of turns, quite a bit smaller, 25,000 divided by 600 on the secondary side. So with all the turns on the primary creates a magnetic flux. That in turn on the other side, as that magnet goes through the conductor, creates a secondary voltage in proportion to what the number of turns are. And of course, as the voltage goes up, the current goes down. Now, power transformers permit utility generated power to be transmitted at very high voltages. The highest I've heard of is 765,000 volt on these massive conductors, going over the hills and mountains and everything else. That can be then reduced in stages to calmer consumer voltages like 120 you plug into. These very high transmission voltages permit relatively low transmission current and thus reduced line voltage. And of course, K is simply, in voltage, kVAC is voltage divided by 1,000. kVA is voltage times amperage divided by 1,000, okay? So 6 kVA is 6,000 volts amps. Ohm's law, we saw earlier, E equals IR. So as voltage goes up, current goes down, which is the big advantage of AC systems. Okay? Let's say we want to transmit 5,000 kVA of power at 500 volt. This means a current of 10 kiloamps over a line, which let's say has 0.005 ohm resistance. The voltage drop will be, working through that equation, 50 volt. We started at 500 transmitting over those lines. We've dropped it down by 10%. Now, if we transmit the same amount of power, 5,000 kVA volt, at 500 kilovolt, which is 500,000, which means a current drop of 10 amp over the same, current flow of 10 amp, that same 10 amp current flow over 0.005 ohm resistance, the voltage drop is only 0.05 of a volt. Well, obviously, if we came into this thing at 500,000 volt and lost 0.05 of a volt, it's insignificant. That's why they can do these super, super long lines without losing that much power, because the voltage is so high. Now, this is what I want to get into, the war of the currents. And there's been books written and everything else. At one time, there was a nasty fight between Thomas Edison and his company, General Electric, and Nikola Tesla, not the car, but the car is named after him, who was partners with Westinghouse, over which was the most suitable approach for distributing power, DC or AC. And it got to be quite nasty, to the point that they had a rogue elephant that General Electric and Edison decided to electrocute using AC to show how deadly AC was, and this kind of nonsense. The ability to utilize power transformers to facilitate high voltage, low current power distribution resulted in AC ultimately winning the war. With DC, they were talking about every few blocks you would have a generating site, which just totally impractical in the long run. So if we look at the system here, transmission of power, generated at a power station, be it thermal or hydroelectric, power transformers jack that up high, into the hundreds of thousands of voltage in a lot of cases, so you can go super long distances. Then when you close in on a city, the voltage is reduced, transformer, and then distributed that, and then reduced yet again to go out to various businesses where it is reduced down to what you want. So typically you could end up at say 25,000 volt, reduced down to 4160 volt, and then as you come off that to your industry at say 600 volt, 347, 600, or to your home at 120, 240, whatever. You can see the point. All of that was pushed, and a lot of very cool stuff was relating to AC was done by Nikola Tesla. In fact, the first significant AC power generation was done at Niagara Falls in 1895. And if you look around, you won't find it without help. There actually is a maple tree and a little memorial to Tesla in a park near the falls, near Niagara Falls. Now, single phase, three phase. Single phase, two wires. And we talked about how the direction of current flips back and forth and the voltage flips back and forth, one being positive, one being negative, back and forth. And it's a sine wave because it's done by a rotating generator, okay? Now it can be without the neutral, or as we see with the neutral, which you get that half voltage effect. Can also be done in three phase. You've actually got three conductors, and each one of them has a sine wave going on, but they're 120 degrees out of phase with each other. Okay, and again, you can have neutrals like to create one from 208, 120, and from 600, 347. Now, delta systems like 120 or 240 volt, there's only three power conductors. Where in a Y system, there is four. There's three plus the neutral. Now, the delta system, as we say, does not have a neutral. What that means is if a power conductor should come in contact with an enclosure, metal enclosure, there is no inherent indication, and the enclosure metal is actually the potential of that conductor. Like, let's say that's happened. A line's come in, it's worn through, and it's actually the conductor is touching a kiosk or whatever. And you walk over and you lean on the kiosk. You might as well be leaning on one of the three hot wires coming in. In fact, if you knew the way one, you could actually be leaning against that thing, touch it, fine. All hell breaks loose, of course, when you touch either one of the other two that aren't grounded. And so then you have to have systems that indicate that this has occurred to give you warning of it so that the situation can be corrected, etc., etc. But it is quite possible to walk up to put your hand on it, and you might as well be line 1, line 2, or line 3. With a grounded neutral Y system, if a power conductor should become in contact with a grounded enclosure, immediately that creates an overcurrent situation. Immediately you have a dead short. And that overcurrent situation, conductor potential to ground, means a protective device will immediately trip. BC Hydro will not provide new Delta services in the province. What has happened classically, like at one time they were fairly common, so there's lots of sawmills running on 460, but basically large installations like that had their own transformers, so they're taking medium voltage from the utility, like say 4160. Therefore, it doesn't bother them because they have their own 480 volt supply as it is. But if you are putting in a pump station, whatever, in British Columbia, you're going to be at three phase. You're either going to be using 120, 208 or 347, 600. They don't care which one. They'll give you either one. But you got to make a decision because that's what you're getting. Now, grounding. What is grounding? Grounding, or earthing as they call it here, is used to establish a common return path for electrical current by means of a direct physical connection to the earth. Yes, the earth can be a conductor. This can utilize either ground electrodes or a grounding conductor cast into the foundation of a building, UFER system. Ground conductors are typically 3 meters long, call it 10 feet, copper clad, driven into the ground, connected, bonded by bare copper wires to all non-current-carrying electrical conduits and enclosures. We talked about a kiosk enclosure. It would be grounded, okay? Or bonded is the expression. An alternate grounding system often utilized with new buildings, pump stations and whatever, is the UFER system developed in 1942 by Army consultant Herbert Ufer for bomb storage vaults near Tucson and Flagstaff, Arizona. That area is bad for ground conduction, so he came up with this idea of embedding an electrode in the foundation of the building, which of course gives you a terrific area in contact with the ground, not just one stupid rod, but the foundation of the building. Very cool. Service sizing. The service sizes typically provided by the utility are 100 amp, 200 amp, 400, 600, 800, 1,000, 1,200, 2,000, 2,500, 3,000. These sizes define the type of service equipment utilized, and the actual loading should be less than these values. Note that ground fault protection is required at and above 1,000 amp. That's a story unto itself. But those are basically the standard services. Now, what happens is your service equipment and everything else will be rated, let's say 200 amp, will be rated 200 amp. And of course, your demand should be less than 200 amp with the pumps and everything else. Utilities will ask what your load actually is, and they will size their own transformers as they see fit, fine and dandy. All to you, though, it's a 200 amp service or whatever. Okay? While the available power supply will often dictate the voltage utilized, as will client preference, should be noted. Now I'm talking about BC Hydro, as I mentioned, either 12208 or 347-600. 12208 is nice because you don't need any transformers to obtain 120 volt for utility or control. With 347-600, the 347 line to neutral in pump station, treatment plants, whatever, is effectively of no use whatsoever. And the higher the voltage, the smaller the conductors. A reasonable rule of thumb is that electrical service size should equal or exceed the total site load plus 50% of the operating current of the largest motor. Okay? Give you an example. Ideally, it turns out 12208 should be utilized up to a 200 amp service. This equates to a duplex station with 25 horse pumps. Let's take a look here. Now, here is a big one. As I always say, why do we use 600 volt and why is it so important? Because at 600 volt, a motor will draw approximately 1 amp per horsepower. In other words, if you have a 40 horse motor, if you look up in the manufacturer's information, it'll be very close to 40 amp at 600 volt. Okay, others are proportional. And if I can do this correctly in the back of my mind, realize as voltage goes up, current goes down. As voltage goes down, current goes up. 600 volt, 1 amp per horsepower. 480, if you take 600 divided by 480, you get a result of 1.25, so about a quarter more. So a 20 horse motor would be 25 amp at 480 volt. Now, as it turns out with 208, if you call that about 200, that's 3 times. So our 20 horse motor would be 600, and if it was 240 volt, actually would be double what it was for 480, so it would be 2.5. So 2.5 times 20, 40, 50. So there's the different amperages just off the top of your head with the different voltages. Now, if we take a look at the example I've given here, 25 horse. So you got two 25 horse motors, and because 208 is, or 200, or we'll get to it, sometimes used as 200, so roughly 3 times, okay? So 2 times 25, that's the base load. But we also need to be 50% of the largest motor, which in this case is half of 25 times 0.3. All that adds up to 188 amp. So we tell Hydro we want a 200 amp service, okay? And away we go. Supersizing. A typical treatment plant specification might read, motors rated from a half to 3 horse shall be suitable for 208 600 volt 3-phase service, while motors rated 5 horse and above shall be suitable for 575 volt. Fractional horsepower motors below a half horse shall be suitable for 120 60 hertz single phase. However, when you get into really big stuff in pump stations, three-phase 208-volt AC motors are often quite practical up to about 30 horse. Um, Conversely, 600 volt, which we'll see this, is actually a 575-volt motor. They're assuming line losses of 25 volts, so the motors are always actually rated, in almost all cases, something less than what the actual power service coming in is supposed to be. Applicable up to about 750 horse. That's always been an argument. Where do you draw the line? And I got advice from somebody who had a lot of experience in it, who suggested 600 volt up to about 750 horse. You can scale that back a bit if you're running 480. The reason being, well, the conductor sizes get very large. In fact, you end up kind of duplicating services. Instead of 3 lines going to the motor, you got 6 and carrying each, line 1 on 2 wires. It's line 2, line 3. The next step above that, the next choice beyond that voltage, is to go medium voltage, which classically today is 4160 volt. The problem with that is it's far more complex to deal with, and the switchgear and wiring are damned expensive. So I think that at 600 volts, 750 horse is a reasonable point. We ended up, I think, we're using 600 horse motors and went with 600. I'm glad we did. Now, when the required service side exceeds what the utility provides, in other words, if they simply haven't got transformers big enough to feed your water treatment plant or whatever, big pump station, then you end up providing the transformer, or the client does, customer-owned service transformer. High voltage up to, say, typical 25 kV, 25,000 volt is provided by the utility, but at a preferable rate. It's a little cheaper buying power from them that way. Why doesn't everybody do it? Because normally they are absorbing the transformer loss, where this way you're absorbing the transformer loss. Now, so then you're into a customer-owned service transformer. These are usually designed to permit future capacity upgrades, okay, usually by cooling. And you see letters like transformer will be ONAN. And in the future, you upgrade it to ONAF, which gives you a higher rating of the unit. Now, what do those letters mean? What they mean is, to begin with, the first of it is, by the way, you're dealing with internal medium and mechanism, external medium and mechanism. That's the 1, 2, 3, 4. So the first, internal. First letter is cooling. Liquid with a flash point less than or equal to 300 C, basically transformer oil. So that's the O. There are options you can work your way up on, but O will be the most common. N, how are you cooling it? Natural convection through cooling equipment and windings, or you can get into different forced variations again. So ON is fairly common. On the external, in other words, the outlet side of the thing, service side, you've got your equipment side. Basically, A, we talk about AN. A is air, W would be water, rare, and the fourth letter is how it's actually being cooled. So ONAN, the last N would be natural convection, just cooled by radiating heat to the air. That's why you see transformers so often with fins on them. F is forced induction. We had a case once with a sewage treatment plant where we were hitting the limit of what it could do by itself, ONAN, but it was set up to take forced induction. So by adding cooling fans with a thermostat to it, we were able to upgrade it significantly and get out of it what we wanted. Here's just a sample of neat stuff. New pump station in Metro Vancouver. If you look at the drawing, you can see the line, and they, by the way, are at 63,000 volt, 63 kV. And you can see how they're separated to prevent an arcing short. Then they all connect into, and all through air. You see this, what looks like a pipe where the arrow is? The three of them come together, and then they go inside to service the pump station. Now, how do we prevent a short there? Because in that pipe is not air. There's a gas with a higher resistance to shorting than air. likely sulfur hexafluoride, okay? Um, and the transformer then takes that power coming in and transforms it from 63 kV, 63,000 volt, to 4160 volt to power these 900 horse TEFC. We'll get later into what that means. ABB Balder. Balder was a good company in Fort Smith, Arkansas that was bought out by ABB out of Europe. So just a little point of interest, okay? Moving right along. Here is sort of your big introduction to how this stuff works. There's 4 elements make up a service to a motor. The first of these is a disconnect. Now, you get exactly the same thing with household stuff. Now, let's pretend you have a vacuum cleaner. Well, a disconnect is the plug. So if you're going to clean the vacuum cleaner, you should go and unplug it first, right? Now, with industrial motors, it's the disconnect switch. Circuit breakers serve the same function if they can be locked out, which we'll get into that later. So disconnect switch or service breaker, now that provides your disconnect needs. And if the motor is remote, then you're required to have another disconnect switch between all this equipment and the motor itself, so within sight of the motor, and you can padlock that or whatever. Okay. And we go through the whole thing. In most households, overcurrent is provided by, now overcurrent is like a short circuit. A kid pushes a hairpin into a wall outlet or whatever. Bang, you've got very high current. That very high current you need to disconnect quickly. You've either got a fuse in your house or a circuit breaker. Nowadays, almost pure circuit breakers. And similarly, industrial, you have to have either fuse or circuit breaker to service that motor, so that in the event the motor shorts out, suddenly high current, you've got something to break that power supply quickly. Now, next one, control. The vacuum cleaner, you got an off-on switch. Industrial motor logic, of course, can be much more complex, but they use a contactor to turn the motor on and off. And last but not least, a lot of household appliances have overload devices that trip. You've got an overload thing on your vacuum, it gets too hot and trips off, you push a button. If you don't, circuit breakers today, most circuit breakers have that ability to respond to an overload. Now, what's the difference between a overcurrent and overload? Overcurrent means massive amount of current flow. Overload means it's more current flow than what the motor was really designed to, and you are overloading the motor itself. Now, if you look at the little drawing on the right, it shows all these things. One on the left bank is a disconnect switch and fuse. On the right is a circuit breaker, which provides both disconnect and overcurrent. Then the contactor, which is turning the motor on and off. Overload relay, which is catching the situation of overload on the motor. Now, contactor to begin with. When you add an overload relay to a contactor, it becomes a starter. And if you add either disconnect and fuse or circuit breaker to a starter, you get a combination starter. See all these fancy expressions you're now experts on? Okay, fine.